this is the end of our mega unit on acids and bases. So I would suggest trying this last particle model on your own and see how far you get. You can pause the video and fast forward if you want to just check your answers, or if you want to talk through it, let's do that too. So I have a 60 milliliter sample of 0.1 molar ammonia, which is a weak base. So we're starting with weak base, which is why the initial pH is around an 11. Then we are titrating it with 0.1 molar hydrochloric acid, strong acid. So if I were kind of setting this up, I've got the base in the beaker or the flask, and I'm adding or dripping in the acid from the burette, which then is why my pH is gradually decreasing over time. I'm adding the acid to the base. Here is our titration curve, and kind of like that previous one, we gotta fix this. You're not adding sodium hydroxide. We're adding HCl. That's why the pH is going down. All right, so I went ahead and counted all the particles that were present in each of these 6 models, and I think we're ready to do this, right? Let's get a balanced equation, because I kind of want to think of this as an ice table as I add the acid to the base. So I'm going to have my NH3, my weak base, and as I add HCl, the chlorine is really a spectator. It's not going to affect the pH at all, but the hydrogen ion will. So as a net ionic equation, we could just add the H plus hydrogen, but I'll kind of put it in parentheses that it comes from the HCl. So the hydrogen and chlorine would have initially had the same concentration, although some of the hydrogen will react with the ammonia. When it does, I'll form NH4+, the conjugate acid. All right, so I'm hoping that we could at least pick out point A, right? Point A should just be the initial weak base. And so I'm thinking that must be this guy. How's that sound? 6 NH3s, and they're trying to show that it's a weak base and that most of the NH3 are little neutral molecules, not ionized if it's a weak base. Okay, so now I'm starting with these 6 NH3s, which I'm always going to have 6 of these guys, and I start to add the hydrogen. So what if I were looking at something like this to be point B, where if I have 2 chlorine, it must have also meant that there were initially 2 hydrogen. The chlorine wouldn't have changed if it's a spectator. And initially, let's say no NH4. Do you kind of see now what would happen? That on the reactant side, it's just a limiting excess situation that whichever is smaller will react down to 0. So that's why there's no H plus ions in this box that I've labeled B. They're the limiting reactant. They've been completely consumed. But I would still have the 2 chlorine spectators left over. But by knowing the amount of chlorine, I can also then determine the amount of hydrogen that would have initially been in the solution. Everybody reacts accordingly. So this is going to go down by 2 to 4 NH3s, and this will go up by 2 to 2 of the ammonium NH4 plus 1 ions. There she is. And look what we have created. A buffer. So we are in this buffering zone at point B, where the pH will change, but not dramatically. I'm getting rid of all that strong acid H plus ion in exchange for a little bit of the conjugate acid, the weak conjugate acid, the ammonium NH4 plus 1 ion, which if it's a weakly acidic particle means that it's really not going to fully ionize to give up those hydrogen. We are essentially removing the hydrogen from the solution. All right, so did you maybe label this as point C? All right, let's see what would happen in my ice table. Let's get rid of these guys. I think I might still have a buffer, so I could leave that. Okay, so initially there were always 6 NH3s. Now I see that there's 3 chlorine, which must have also meant that there were 3 hydrogen ions initially. Initially, no NH4 plus. All right, so my limiting reactant is still the hydrogen. This guy goes down to 0, and everyone reacts accordingly. Plus 3, up to 3. Not only do I still have a buffer, but I have the special buffer. I have the magical 1-to-1 ratio buffer. Point C is special. It's the halfway point. Or sometimes we call it the half equivalence point. Not only do we have a buffer, but when we have this 1-to-1 ratio buffer, the pH equals the pKa. Because then I'm going to end up adding the log of 1, and the log of 1 is 0. So essentially, then this is an important point in the titration, where the pH equals the pKa. It's a way then of identifying an acid if, let's say, it were an unknown. Actually, in this case, it would be like an unknown base, where the pH would equal the opposite log of the ammonium ion. And so here, if I can kind of estimate, if I estimate that across, let's see here if I get back to this guy. I don't know. I mean, I get that it's not exactly 9, but let's just pretend that it was 9. To make it easy, let's say it was 9. So then we could say then that the pKa equals 9, or in other words, the Ka of the acidic particle in the buffer, if I'm looking at Ka, it's the acidic particle in the buffer, which is the NH4 plus 1 ion. That must be about 10 to the negative 9. So if I had a list of potential acidic particles, weakly acidic particles, I could say, yep, this was the titration involving the NH4 plus ammonium ion. I would also be given then the Ka values so that I could match up my Ka to the potential weak acids. It's a really important point in the titration. There's 2 important points. This is one of them. Awesome. Then, hopefully, going ahead, you labeled point D. Here's what happens at point D. Some of this I can kind of keep in there. I think we're going to have a buffer still. Looks like there's 4 chlorine, which must have also meant 4 hydrogen. Still my limiting reactant, so this will go down to 0, and this will go down to 2, and up to 4. I still have a buffer, but it's a little bit more on the acidic side. The ratio is changing. So as I keep adding more acid, I still have a buffer, but I'm going to have more of the NH4, the acidic particle in the buffer. And so what I have on this whole point on the titration curve, like anywhere in here, we call that the buffering zone or the buffering region. We'll call that the buffer zone. It's that highlighted point in yellow where I'm adding strong acid, and yeah, my pH is dropping a little bit, but not like if I were adding strong acid to water. My pH would drop substantially. And it's because I'm forming this weakly acidic ammonium ion. Fantastic. All right, so now let's see if we found the equivalence point. Okay, so if I get rid of this in my ice table, did we find the equivalence point? The equivalence point is point E. How about this guy? Where it looks like there are 6 chlorine, which would have also meant 6 hydrogen. And so, yep, when I have equal moles, or here equal particles, these guys are going to react completely. And they both go down to 0. So that really all I have at the equivalence point, yep, it's that conjugate acid, which then is why the solution, even though I'm at the equivalence point, the solution is not neutral, because I'm not just forming water and a bunch of spectator ions. I've got my spectator chlorine, which is neutral, but then the NH4 ammonium ion, that guy is acidic. So my pH at the equivalence point is slightly acidic. So this is the other important point on the titration curve, the equivalence point. The equivalence point is helpful in knowing how much acid or how much base was used to reach that equivalence point, that point where I have the molar ratio from the balanced equation. I can just follow that down to get the volume needed. And if I knew the volume and I knew the molarity, I could figure out moles of this case, acid, needed to reach the equivalence point. And if I follow it across, I would maybe get like a pH of about 5, confirming that I have a solution that includes a weakly acidic particle. Awesome. And then finally, I'm hoping that we labeled point F. That's all that's left, right? That process of elimination. Hopefully point F is when we've gone beyond the equivalence point. So at this point, it looks like there's 8 chlorine, which meant that initially there would have also been 8 hydrogen. Yep, now I'm to the point where that hydrogen ion was in excess, and the limiting reactant became the NH3, the ammonia. Goes down to 0, and everyone reacts accordingly. 6. See, now my pH is pretty acidic. My pH is like a 2. I do not have a buffer. That is not a buffer. Not a buffer. Because I've lost all of my weak base. Instead, all I have is 2 particles that are acidic. I've got really strong acid coming from the excess hydrogen, and then I've got the weakly acidic NH4 ammonium ion. So there's no doubt in my mind that this final solution would be acidic when I go beyond the equivalence point at point F.